Welcome to the Deep Dive, your shortcut to being truly well-informed. Today, we're diving into, well, one of the really compelling frontiers in AI. We're talking about systems that go beyond just spotting patterns. They're starting to actually reason, to abstract, kind of like humans do.
Exactly. It's about that ability to see just a few examples, figure out the underlying rule, and then apply that rule to something totally new.
Right, which is the whole idea behind the Abstraction and Reasoning Corpus, or ARC challenge. A benchmark that's really trying to push AI past simple data interpolation towards, genuine understanding.
That's a tough one.
So our mission today is to unpack a very recent preprint. I mean, it just came out August 13th, 2025.
Hot off the presses.
Yeah. Channel-wise MLPs improve the generalization of recurrent convolutional networks by Nathan Breslow. We're going to explore how what seems like a really small tweak, architecturally speaking, can actually lead to some surprisingly big improvements in generalization.
Fascinating stuff.
So the core question is really this. Can one tiny change in how a network processes information really boost its ability to handle tasks it's never properly seen before? That out-of-distribution generalization.
Yeah, the OD performance. That's the key metric here.
Let's peel back the layers.
So, as you said, the ARC challenge is fascinating because it flips the usual script. It's not about, drowning models in data.
But not the massive data sets we usually hear about.
Oh, instead, it's trying to mimic how humans learn, needing networks to find these abstract rules from just a handful of examples. It's not memorizing. It needs what the paper calls program-like computation.
Like figuring out the steps.
Exactly, like a mini program. And symbolic manipulation, working with concepts, not just pixels.
And this ability to generalize, it's not just for ARC, is it?
Oh, definitely not. These properties, like handling different input sizes, strong generalization, they're crucial for tons of other vision and reasoning tasks.
Especially where you don't have perfect data or things change.
Precisely. And the good news is recurrent convolutional networks, they're actually showing some real promise here. There's work like Schwarzschild et al., showing them scaling from, say, 9x9 mazes up to 13x13 ones.
That's a decent jump.
Yeah, and even improving on chess puzzles. And we're seeing things like adaptive depth and transformers helping with generalization on tasks like binary summation, too.
So the field is moving towards architectures that can think a bit more flexibly?
Slowly but surely, yeah.
Okay, let's unpack this specific paper then before we get to the breakthrough part. What exactly is DARC? That's the baseline network they use, right?
Right. DARC. It stands for Depth-Aware Recurrent Convolution. And it's actually a pretty simple recurrent convolutional structure, relatively speaking.
Simple how?
Well, it starts with a linear embedding layer for the input. Then the core is this looped convolution. It basically keeps refining the input grid, adding its output to what's called a residual stream.
Ah, the residual stream. Like it remembers the previous steps?
Sort of, yeah. Think of it like adding detail progressively. Each pass builds on the cumulative changes.
Okay.
And this recurrent block, it repeats n times. And n isn't fixed. It depends on the input grid size. Usually about twice the max of height or width.
Ah, so it adapts. That sounds pretty useful.
It is. That's one of its strengths.
So what are the main advantages of DARC as a starting point?
Well, that variable input size is a big one for generalization, like we said.
Makes sense.
It's also meant to be easily interpretable because of that residual stream. You can kind of see how it's building its solution.
Right.
And importantly, it works pretty well even when it's small. It keeps its expressive power at extremely small scales. Good baseline for these kinds of tasks.
Okay, so that's DARC. Now, this is where it gets really interesting, right? The paper talks about a minimal architectural difference in DAMP that has this tremendous impact. What exactly is that change, and why is it maybe surprisingly simple for the results they got?
Yeah, Aware Multi-layer Perceptron. It builds right on DARC. The key change, and it is simple on the surface, is adding a single gated multi-layer perceptron, an MLP, right after the depth-aware convolution in that loop.
An MLP, okay. And it processes things channel-wise. You mentioned that and GLU gating. Can you break those down a bit?
Sure. So channel-wise means this MLP looks at each feature map or channel coming out of the convolution kind of independently.
Like if one channel tracks edges and another tracks color.
Exactly. The MLP learns separate transformations for edges, colors, textures, whatever features the convolution learned without mixing them up right at that point.
Okay, and the gating.
The GLU gating, it's an activation function, but it acts like a smart gate. It controls the flow of information based on relevance. It helps add nonlinearity effectively without making things overly complex. Found to be quite effective.
Got it. So it's a more targeted way of processing the convolutional output. But the author said the impact was tremendous and surprising. Why surprising, given that convolutions already mix channels?
That is the interesting part. You'd think the 3x3 convolutions already do plenty of nonlinear channel mixing.
Right.
But the authors found that adding this specific channel-wise MLP gives the model a much, much richer way to combine features internally. It's like giving it a more sophisticated toolkit for understanding abstract patterns across channels. So the surprise was just how much more expressivity this single, relatively simple MLP added, especially since it leads to such a big performance jump, even when you match the total number of parameters.
Parameter match, that's important. So it's not just making the network bigger.
Exactly. It's about the type of computation.
Okay, so how did they test this? You mentioned the REARS dataset.
Yes, REARS. It's procedurally generated, which is great because you can control the difficulty.
Right.
So they trained the models, both DARC and DAMP, on easier tasks difficulty between 0.3 and 0.5. Then they evaluated them on harder tasks, difficulty 0.55 to 0.8, to really measure that out-of-distribution generalization.
Pushing them beyond their comfort zone.
Precisely. And they picked 185 specific REARC tasks that fit certain criteria, like keeping the grid size the same and being fast to generate.
And crucially, you said they started from scratch for every task.
Yes, random initialization for every single task, no pre-training carryover between tasks, really isolates the architecture's ability on that specific problem.
Okay. And training setup. Anything notable there?
Yeah, they used 2048 batches, 16 examples each, so about 32,000 examples total per task. And they mentioned using the muon optimizer, which apparently worked better than AtomW for them here.
Interesting optimizer choice. Now, you mentioned something fascinating about the grading.
Ah, yes, the exact match grading. This is critical. It means if the output grid is off by even one single pixel, the score is 0. No partial credit.
Wow, that's harsh.
It is, but it leads to this bimodal distribution of results. Models either solve a task perfectly 100% or they get 0%.
All or nothing.
All or nothing. It really measures if the model truly understood the underlying rule.
Okay, so with that super strict grading, how did DAMP actually stack up against DARC?
The results are, well, pretty stark, especially on the harder tasks. So for the in-distribution tasks, the easier ones they trained on, DAMP got a median accuracy of about 92%.
Pretty good.
Yeah, compared to DARC's almost 79%. So a nice improvement there already.
Okay.
But the really striking difference, the real aha moment, is the out-of-distribution median accuracy.
The hard stuff.
The hard stuff. DAMP hit 14.58%. DARC, just 2.34%.
Wow. From 2% to almost 15% median accuracy on harder unseen task variations.
Exactly. It's a huge leap, a really profound difference in generalizing.
That's incredible. What about the mean accuracy? Does that tell a similar story?
It does, though the numbers are higher overall because some tasks are solved perfectly. For ode mean accuracy, DAMP went from DARC's 31% up to nearly 39%, which translates to solving about 8% more grids completely correctly on average.
And this was still parameter matched.
Parameter matched. DAMP actually had slightly fewer parameters than the DARC model they compared it to, so it's definitely not just about model size.
So these results were clearly significant then.
Oh, absolutely. Statistically significant, p-values way below 0.001. The confidence intervals didn't come close to 0. It's a robust finding.
But we should probably temper excitement just a little, right? Neither model is cracking RC completely.
Absolutely right. Important caveat. The authors are clear. Both methods still fail completely on a decent chunk of tasks, like 23% in distribution and over 38% out of distribution.
Still a long way to go.
A long way to go. And mean accuracy on the hard ode tasks is still under 40% for both. But that jump DAMP made in generalization is undeniable. It points somewhere useful.
So let's talk about that. What does this mean for the bigger picture? Why should we care about this specific improvement beyond just DARC and DAMP?
Well, if you connect it to the broader goals, like making real progress on ARC or similar challenges, this matters. It suggests that focusing on how information is mixed and processed internally, even with small architectural changes, can yield big gains in generalization from limited data. And these architectures, especially DAMP, they offer kind of a novel angle on neural program synthesis.
Neural program synthesis? AI writing code, basically. What are the usual problems with that, particularly with ARS?
Yeah, the traditional approach is often getting a network to spit out, say, Python code. But there are two main problems. First, not all RRC tasks really map nicely onto clean Python code. Some feel more intuitive, pattern-based.
Right.
Second, and this is a big one, Python code isn't differentiable. You can't easily tweak it using standard AI training methods like backpropagation, which means you miss out on techniques like test time training.
Test time training. That comes up a lot with ARC. Remind us why that's so important.
It's super powerful for few-shot problems like RRC. The idea is you get the test examples, the puzzle you need to solve, and you actually fine-tune the model on those specific examples for a few steps right before making the final prediction.
Like a quick cram session just for that puzzle.
Exactly. It lets the model adapt on the fly. But you can't really do that effectively if your output is a rigid block of Python code. That's the hurdle.
Okay, so how does DAMP fit in as a potential solution or alternative path?
Well, instead of generating code, you can use a hypernetwork.
Hypernetwork.
Yeah, it's a network that generates the weights of another network, the target network, that will actually solve the task.
So it generates the solver network itself.
Precisely. And because that target network is a neural network, its weights are differentiable, so you can use test time training on it.
It's ever workaround.
It is.
Yeah.
And DAMP looks like a really promising candidate to be that target network. It's expressive enough to solve a good variety of tasks based on these results.
Right.
But it's also small enough that generating its weights with a hypernetwork seems feasible. Plus, it handles variable inputs, performed well across many tasks with one configuration. And we know hypernetworks work pretty well for generating weights in other areas, like MLP classification.
So DAMP hits a sweet spot. Powerful enough, small enough, and differentiable.
Seems like it, yeah.
But again, the authors themselves add a note of caution, don't they? This isn't solving AGI.
Absolutely crucial clarification they make. This is not a general solution to RC AGI. True general AI would need to show few-shot generalization to totally new kinds of tasks it's never encountered.
Okay.
What this shows is strong out-of-distribution performance on tasks it has been trained on, just much harder versions. It's generalizing within known task types, just to greater difficulty.
So it's a step, a significant one perhaps, but not the final leap to general reasoning.
Exactly. The real takeaway isn't that DAMP is AGI, but that its internal workings, its inductive biases, seem much better aligned with the kind of reasoning needed for ARC compared to simpler recurrent convolutional nets.
It's evidence we're barking up a promising architectural tree.
Precisely. It tells us this type of architectural enhancement, focusing on channel mixing and internal processing, is a very fruitful direction for tackling abstract reasoning.
Okay, so to recap this deep dive, a simple change, adding channel-wise MLPs to a recurrent convolutional network, DARC, created DAMP. And this seemingly small tweak yielded really substantial performance gains, especially on those harder, out-of-distribution tasks, better generalization.
A big jump, yeah.
And this points towards new ways to think about neural program synthesis, maybe using DAMP as a target for hypernetworks.
It opens up some interesting possibilities there, definitely.
Which leaves us with a final thought, maybe. If such a subtle tweak, just adding that MLP, can unlock so much better abstract reasoning, what other seemingly small changes are lurking out there?
What other ways of tweaking how networks process and mix information internally could lead to even bigger breakthroughs, especially for those really complex human-like problems?
A fascinating question indeed. Food for thought as AI keeps evolving. Thanks for joining us on this deep dive.